Today's topic will be balancing chemical equations. The objective that will be covered in this topic will be to use both ionic and molecular equations to represent chemical reactions. We will include state symbols. Let us begin. Now, when balancing equation, we must ensure that the number of atoms on one side is equal to the number of atoms on the other side. To do this, we follow the law of conservation of matter, and it states that matter can neither be created nor destroyed during a chemical reaction. So all that happens is that the atoms are rearranged. So, in a chemical equation, the atoms or ions are rearranged to form products, but the total mass of the reactants is equal to the total mass of the products. Now, chemical reactions can be represented by using chemical equations. Now, in a chemical equation, we have reactants and we have the arrow that is saying that what is being produced, and then we have the product. Look at this example of a chemical reaction. Magnesium is reacting with oxygen to produce magnesium oxide. You can see that on the left of the arrow, you have magnesium atom, which is solid, reacting with oxygen molecule to produce magnesium oxide, again, which forms a solid. You'll see that the magnesium will combine with the oxygen and they are rearranged to form the product. Now, we normally count the number of atoms on the left and count the number of atoms on the right, and they must be equal, and then we will have a balanced equation. So initially, it was one magnesium present here and one there, and then one oxygen, but we realize that there are two oxygen atoms here, so we must put 2 in front of the magnesium oxide to form 2 MgO. Now that we have 2 MgO here, we must put 2 in front of the magnesium. Now this is a balanced equation. Balancing equation is a trial and error. So you will try until you get it right. Most times you will not get it right on the first try. So don't worry about what you're doing, getting it wrong the first time. Just keep going. Here we have another equation. And here, hydrochloric acid is reacting with sodium hydroxide. We form or produce sodium chloride and water. So the atoms in the reactants are rearranged to form the atoms in the products. And you'll see that HCl here is no longer over here because the HCl broke up and combined with sodium to form NaCl, and the OH combined with the H to form water. But the total mass here is equal to the total mass here. Let's check to see if our equation is balanced. 1 sodium on the right, 1 sodium on the left. 1 Cl on the right, 1 Cl on the left. 2 hydrogen on the right, 1 here and another one here, so we have 2 on the left. And 1 oxygen on the right, 1 oxygen on the left. So this is a balanced equation. Now that we have balanced this equation, let us see if the law of conservation of matter holds to be true. Let's check. We know already how to find the mass numbers from the periodic table. So the mass number of H is 1 and the mass number of chlorine is 35.5. So we will add those values. Sodium is 23, oxygen 16, hydrogen 1. So on this side, for HCl, we have 36.5. For sodium hydroxide, we have 40. On the right, sodium chloride, its mass worked out to be 58.5 and the mass of water is 18. So you'll see that when we add up these masses on the right and we add up the masses on the left, we get the same mass on the right, that is the same mass on the left. And so the law of conservation of matter was proven, that matter cannot be created nor destroyed. Every time you balance an equation, it is very important to put in your state symbols. Now, let's look at the balance equation in terms of ratio. The ratio is the number that is placed in front of each molecule or compound in the equation. And the term we use for that is stoichiometry. A balance equation has the same number of atoms of elements on either side of the equation. And you must place in your state symbols. So if an atom or a compound is a solid, you put a small s in bracket for solid. If it is a liquid, you put a small or common L in bracket. For gases, we put a common G in bracket. And if we have an aqueous salt, we put AQ in bracket. We will have a better idea of aqueous substances when we do acid bases and salts. Here are some basic steps to follow when balancing any equations. 1. Write the correct formulas for all reactants and products in the reaction. Let's try this simple one. Sodium carbonate plus HCl produces sodium chloride plus carbon dioxide plus water. Now, it's very important to write the correct formula, because if your formula is incorrect, then your balancing will automatically be incorrect. So that's step 1. Step 2, the reactants are written on the left and the products are written on the right of the arrow. We are now going to count the number of atoms of each element in the reactants and the number of atoms in each element in the products. So we'll start by looking at what's going on the right of the equation. Here we have 1 sodium atom, but over here on the left we have 2. So to ensure that that is balanced, we will put 2 here. Now I have 2 sodium atoms here and 2 on the left. Let's move on. This number in front is saying that I also have 2 Cl atoms. Over here, I have only 1 Cl. So I will put 2 in front. So notice we use whole numbers when balancing equations, and they are placed in front of the molecules or compounds. And that is your stoichiometric ratio. So it is always helpful after placing a number in front of the compound to start over, to ensure that your other elements are being balanced out correctly. So 2 sodium, 2 sodium, 2 Cl, 2 Cl. Now we're now on to carbon. 1 carbon here, 1 carbon here. 2 oxygen and 1 here, 3 oxygen atoms. Over here we have 3. So nothing is wrong with our oxygen. The same number of oxygen on the left is the same number on the right. We move on to hydrogen. And we have 2 H's here, and over here, this number in front is saying now that we also have 2 H's on the left-hand side. In terms of polyatomic ion, we can count them as 1 if they appear on both sides of the equation. Example, suppose I have zinc plus copper sulfate, and that produces zinc sulfate plus copper. Counting our atoms on the right, I have 1 zinc here. So nothing is wrong with our zinc atom. Instead of counting separately the atoms in the polyatomic ion by saying 1 sulfur and then 4 oxygen, we can treat this as 1. So I could say 1 SO4 on the right, and on the left I have 1 SO4. And then we have 1 copper and then 1 copper. So we're balanced. So we could separate it if we wanted to. So I could say 1 sulfur, 4 oxygen, 4 oxygen. But for polyatomic ion, if it appears on both sides of the equation unchanged, then it is very simple for us to treat the polyatomic ion as one thing and just count it as 1 instead of separating the atoms in that polyatomic ion. Just as a reminder, when we balance with coefficients, which is our whole numbers, they are normally placed in front of the formulas. But remember that if the coefficient is 1, then we would not put that number in front of the formula. Only if the number is greater than 1, then we put that number in front of the formula. Of course, we will check each atom or polyatomic ion to be sure that the equation is balanced. And then we make sure that all the coefficients are in the lowest possible ratio. So we would not have, for example, A plus B to produce A, B, and have, let's say, 12 here, 3 here, and 4 here. Now, finally, we should ensure that all the coefficients are in the lowest possible ratio. By that we mean, if we have 2 in front of A, 4 in front of B, and 12 in front of AB, we would not leave it as 2, 4, and 12, because this can be simplified in terms of its coefficient. So 2 into 2 will be 1, 2 into 4 will be 2, and of course 2 into 12 would be 6. So the correct equation that we would write would be A plus 2B to produce 6AB. Just to try and show you in terms of what do I mean by the coefficient being in its lowest possible ratio. Don't worry about looking at the atoms and saying, but wait, how come we have 6A here and over here we only have 1? That's not balanced. I'm just trying to show you that in terms of coefficients, they should be in its lowest possible ratio. So don't worry about what is present here for now. This is just trying to show you an example of the coefficients. So focus on the 2, the 4, and the 12. Here we have some general reactions. And these reactions you must know for this syllabus, because these reactions you will be seeing over and over again. Now we have some molecular equation and we have some ionic equations. So let's start with magnesium plus oxygen produces magnesium oxide. Now this is a general reaction in terms of metals will react with oxygen to produce metal oxides. I could replace sodium here instead of magnesium, so sodium with oxygen would give me sodium oxide. Of course, the formula would be different. So substance plus oxygen give you the oxide of that substance. Metal plus water will produce the metal hydroxide plus H2 gas. And it is very important that anytime you write equations, that you balance them and you put in the correct state symbols. Metal plus acid produce salt and hydrogen gas. Here we have 1 magnesium, 1 magnesium. 2Cl, over here it was 1 initially, so we put 2 in front of the HCl to get 2Cl. 2 H's, over here we have 2 H's, and so now we are balanced. In terms of the ionic equation, you will learn shortly when we start acid, base, and salts that the spectator ions are removed And so the ions that did not take part in the reaction are the ones we call the spectator ions. So you will not see them in an ionic equation. Only the atoms or ions that take part in the reaction you will see. Here is an acid-base reaction. An acid-base always produce a salt and water. Again, you must ensure that the equation is balanced and the correct state symbols are used. Sodium hydroxide plus sulfuric acid. Earlier you saw a base with an acid. This is also an acid-base reaction. The only difference is this base is called an alkali because it is a base that dissolved in water. So this is an aqueous solution of an alkali. So acid and base produce your salt and water. This is an ionic equation for an acid-base reaction. So again, you see that the sodium would be the spectator ion, so the sodium would not be present here, and the sulfate in this case is a spectator ion, and so it is not present here, and we produce the water. Carbonates plus acid produces your salt, carbon dioxide, and water, and this is general for all carbonates with acids. And this is your ionic equation for a carbonate reacting with an acid to produce your water and carbon dioxide. Notice that you don't see the calcium or the Cl or the salt because the spectator ions were cancelled and removed. So this equation here would be the same equation written for any carbonate reacting with any acids. The same reaction would be for a hydrogen carbonate reacting with an acid. You produce a salt, carbon dioxide, and water. The only difference is your ionic equation will be a bit different because this time it is a hydrogen carbonate and not a carbonate. So basically, when you have a chemical reaction and it is taking place in an aqueous solution, the ions will separate and rearrange themselves. But not all ions are responsible for taking part in the reaction. Or not all the ions are involved in forming the products. So the ones that are not involved in forming the products, we call those the spectator ions. They are merely there to spectate, to sit in the stands and watch, but not taking part in the actual reaction, which is the game. So in an ionic equation, we would separate the ions that are aqueous, and then if our ion is aqueous on the right and aqueous on the left, then we would cancel those ions. So here, in this case, I'm going to separate the ions here that are aqueous and leave the ion that is solid. So Ba, aqueous, would form 2 plus and Cl would form minus. Now notice I must ensure that I have mass balance and charge balance. So because Ba is 2 plus, I must have 2 Cl minus to balance out that positive charge. And then I am going to separate sodium. So I have Na plus, also SO4 2 minus. But since I have 2 minus, I must have 2 plus here. Arrow, I cannot separate barium sulfate because it is a solid. So I cannot separate it into its ions. I can separate sodium plus and Cl minus, and these are aqueous ions. So 2 in front there, 2 in front there. So when you look at your ions and you put in your state symbols, as long as you are an ion, your state symbol is aqueous. So if I am aqueous here and I am aqueous over here, I am unchanged, and therefore I would be a spectator ion. But in the case of barium, barium here is aqueous and barium here is solid, so barium ion is not a spectator ion. It is actually taking part in the chemical reaction. Moving on to Cl minus. Here we see where Cl minus is aqueous here and Cl minus is aqueous here. So being that it is unchanged, it is saying that it is a spectator ion and did not take part in the chemical reaction, so we must remove it. So I will remove Cl minus because it is a spectator ion. Sodium ion aqueous here, sodium ion aqueous here. It is also a spectator ion, so we can eliminate sodium ion. Sulfate ion aqueous here. Over here, the state changes to solid. Therefore, this ion took part in the reaction in forming barium sulfate solid. So we cannot remove it. And then we will now write the equation Ba2 plus SO4 2 minus aqueous to form the barium sulfate solid. And this is our ionic equation for this molecular equation. Let's take a quick look at these two other examples. Aluminum sulfate plus sodium hydroxide will produce aluminum hydroxide plus sodium sulfate. Note the state symbols aqueous, aqueous, solid, and aqueous. So if we separate the ions in aluminum, you'll see that it changed from aluminum aqueous to aluminum solid. So we cannot remove aluminum from the equation because it is taking part in the reaction. So aluminum ion will be Al3+, and it forms aluminum hydroxide solid. The sulfate is aqueous here, and the sulfate here is also aqueous, so that we can eliminate as a spectator ion. Sodium also, because sodium is aqueous here, and on the right, sodium is also aqueous. Remember, we must ensure that we have both mass and charge balance when working out ionic equations. So what are we left with? Hydroxide is aqueous here, but here it is a solid. So the ionic equation for this reaction would be Al3 plus 3OH minus to produce AlOH bracket 3, which is solid. Ionic equations are very useful for simplifying precipitation reaction. And what we mean by precipitation, simply, if you add two ions in an aqueous solution, they will combine to produce a solid out of solution. And that is what we mean by precipitation, a solid precipitating out of solution. We can also look at acid-base reactions. And if you look at this acid-base reaction, you'll see that sodium is a spectator ion on both sides. It remains aqueous. OH minus aqueous here, but over here we have water liquid, so we can't remove OH or H. But sodium and Cl are spectator ions that we removed. So all reactions between strong acids and strong alkalis will have the same ionic equations. Remember, all carbonates reacting with acids will have the same ionic equation. So in the exam, if they ask you to write the ionic equation for any acid with any carbonate, you simply write H plus 2H plus CO3 2 minus to produce carbon dioxide and water. So finally, for a quick recap, you see that here we have a balanced equation. The reactants and products are your A and your B in capital letters to produce C and D, which are your products. And of course, the mole ratio or the stoichiometric ratio is represented by your common letters in front of your capital letters. And that is what we use to balance the equation. And here is an example. The balance equation here is 2 calcium plus oxygen to produce 2 calcium oxide. So the reactants would be calcium and oxygen, and the product would be calcium oxide. The mole ratio or the stoichiometric ratio will be 2 to 1 to 2. If we understand how to balance equation, then Doing mole concept will be very easy for you because we use stoichiometric ratios in calculating moles, volumes, and masses.